Welcome. Now we're going to be looking at evaluating limits analytically. But first, let's look at this statement. What's the difference between the following two statements? F of x equals L, and the limit of f of x as x approaches a equals L. I want you to include this in your notes, and it's very important that you know the distinction between these two statements. So in general terms, f of x equals L means first of all, the function exists at x, and not only does it exist, the value of the function when x equals x, sure, it's just said f of a equals L, I think. So the value of the function when x equals x is equal to, oh, I don't like the way that word looks. Let's see if I can just make that smaller. When x equals x, let's put a comma there, is L. Right there, we can get it on one line. All right, so f of x equaling some value, first of all, tells us the function exists at that value, and not only that, it tells us exactly what that value is. The limit of f of x equals L means the value the function approaches as x approaches a from the left and as x approaches a from the right equals L. It tells us nothing about f of a. We know nothing about that, right? So we have three different scenarios that could occur, right? And let's look at our three different scenarios here. All right, so that's going to be A. So I could have this. All right, could have maybe a graph like that. All right, so there is f of a is right there. And notice as we approach from the left-hand side and from the right-hand side, we're approaching the same value as f of a. So in this case, the limit, actually let me write f of a first. F of a is equal to the limit of f of x as x approaches a. All right, so the limit and the value of the function are exactly the same. It could be that we have this second scenario. Right, so there's A again, and I do that. Right, and so if you look here at A, f of a, that doesn't even exist. Right, that does not exist. That's a hole in our graph. But as we look from the left-hand side and the right-hand side, our limit does exist. Right? So the limit of f of x as x approaches a, that exists. And it is not equal to the value of our function at a. Oops, I'm supposed to say f of a. Right? So it could be that the limit and the value of the function are two different things, and the function doesn't even exist. It could be we have a third option here. Third scenario. Right? So here's A again. Oops, I guess I picked up the green pen too quickly. Right, so I have this. Right, so here, f of a does exist. However, f of a does not equal the limit as x approaches a of f of x. All right, so it could be, can I make that a little nicer looking? So it could be that our limit exists, but the value of the function doesn't exist. So here you can see as we approach from the left-hand side and the right-hand side, that's the limit of our function. And notice it's not the same as the value of our function, which is down here, right? So it can be that we can have three different scenarios here, right? The limit and the value of the function are the same. The function doesn't even exist at that point, but the limit still exists. Or the function exists, but it's not the same as the value of the limit. Right? Of course, we could have another scenario where the limit doesn't exist, but we're looking at when the limit does exist, and the difference between f of x equaling a value and the limit equaling the value. All right? So notice that the value of the function and the limit, they're not the same thing. And it's a very important distinction, and that you really need to know the difference between those two statements. All right? So include this in your notes. Of course, if I go too fast, you can always pause me. That's the nice thing about having this taped. So a limit describes what happens to the function as it gets closer and closer to a certain value of x. The function doesn't have to have a value at that x for the limit to exist. So just because you know something about the limit doesn't mean you know anything about the value of the function unless you've got some more information about that function. And just because you know the value of the function doesn't mean you know anything about the limit of the function unless you have more information about that function. All right, so we're going to be looking at evaluating analytically. Before we do that, though, let's review one-sided and two-sided limits. And this is also in your notes. So the relationship between one-sided and two-sided limits. The two-sided limit of a function f of x exists at a if and only if both of the one-sided limits exist at a and they have the same value. That is, the limit as limit of f of x as x approaches a is equal to L if and only if the limit of f of x as x approaches a from the left-hand side is equal to the same value as the limit of f of x as x approaches a from the right-hand side. So for a two-sided limit to exist, both one-sided limits have to exist. Right? So if we're at an endpoint of some function, that's going to be a one-sided limit only. Right? So if we're at an endpoint, that we can't have a two-sided limit. Right? That's a one-sided limit only. So both one-sided limits have to exist. So endpoints are automatically eliminated from being a two-sided limit. But if we're not at an endpoint, if both one-sided limits exist and both one-sided limits approach the exact same value, right, then our two-sided limit exists. So just a little review on one-sided and two-sided limits. All right, so using one-sided limits, we can say that the limit of f of x is equal to L if and only if, as I say, limit of f of x as x approaches a is equal to L if and only if, that IFF means if and only if, the right-hand limit and the left-hand limit exist, and they equal the exact same value. That's the properties of limits. The limit of f of x as x approaches c does not depend on the value of f at x equals c. Right? We had the three different scenarios, right? It could exist. Right? So back here we talked about, here we go. So sometimes, right, the value of the function and the limit's the same, and sometimes it's not. We had two different examples where it's not the same. But sometimes it is the same. When it is, we can use substitution because the value of the function is exactly the same as the limit of the function. Right? So in cases where the value of the function equals the limit of the function, the limit can be evaluated by direct substitution. So the limit of f of x as x approaches c is going to be equal to f of c anytime we can use direct substitution. And we're going to be able to use direct substitution when we have a well-behaved function. It's a good function, and it's a well-behaved function when it's continuous at c, the value that x is approaching. Now, a function does not have to be continuous everywhere to be well-behaved at and continuous at our point. Right? So as long as the function is continuous at whatever value we're evaluating the limit at, then we can use direct substitution. And so that's a really easy way to find a limit. Right, so some basic limits, and this is in your notes. Let b and c be real numbers and n be a positive integer. Right, so the limit of b as x approaches c is equal to b. This is just a horizontal line. It has the same value everywhere. Right, so actually it wouldn't matter what value x was approaching. The limit's going to be b, right, because it's just a horizontal line. And we'll take a look at an example. If we have a linear function or even a polynomial function, right, those are continuous functions everywhere. And so the limit of x as x approaches c, we can just substitute in. Right? Also, exponentials are continuous everywhere. Right? So if we have something raised, so n just means it's any integer at all. Right? So exponential functions are continuous functions. Okay? So long as n is a positive integer, right, then we can whatever x approaches, right, we can just substitute that in, and we can evaluate that one by direct substitution. So let's take a look at some examples. Right, so evaluating basic limits. Right, and so by the way, why this had to be back here had to be a positive integer. Right, so imagine that it's negative 1/2. That's our exponent. Right, so let's just say we have the limit as x approaches negative 2 of x to the 1/2. Right, well, now I can't substitute in. Right, it won't work in this case because negative 2 to the 1/2, right, that limit's not going to exist. The number here doesn't exist. Right? This is a one-sided limit. 0 would be the end point. Right? So we have a one-sided limit at 0, and we'd have no limit because the function doesn't exist for anything negative. Right? So that's why it says a positive integer. Right? So, but some places, right, that would be continuous. We could plug in, but just not at every value. So in this case, here's an example that a value that wouldn't work. So that's why it says positive integer, because it's not true for all exponents all the time. But it is true for positive integers. Right? So and there's an example. Right? So that one wouldn't work at all. So here we have 3 examples. The limit of 3 as x approaches 2, and that's equal to 3. So just to kind of remind you what that would look like. Such a straight line there. Let's see how straight this one looks. Well, it was straight when I drew it. There we go. So if you use your imagination, that there's no little glitch there. All right, so we're looking at 2. There's 2. All right, so as we approach from the left-hand side and we approach from the right-hand side, no matter what, it's going to be equal to 3. As a matter of fact, it could approach anything, it's going to be equal to 3. Here we have an example of a linear function. So the limit of x as x approaches -4. Right. There's our function graphed. So as we would approach from the left-hand side and the right-hand side, we would approach the same value, -4. And then one more, the limit of x squared as x approaches 2, and this is the last time I'm just going to draw graphs. We'll be evaluating with substitution later on. And so we're looking at 2. So here's what the graph looks like. So we have 1, 1, and -1, 1, and 2, 4, and -2, 4, and then it would continue with 3, 9, and -3, 9. Oops, what happened to my parabola? We'll just ignore, there's not really enough room for this point. We'll just ignore that one. So here's our parabola. Kind of went out kind of far there. We'll move that point there. All right, so here is 2. And so as we look, of course this would be 4. As we look from the left-hand side and the right-hand side, right, the limit of x squared as x approaches 2 is 2 squared or 4. So now we don't have to draw the graphs on these. I just wanted to kind of show you and relate it back to our graphical limits. We can use direct substitution because these are well-behaved functions. So properties, here's some more properties of limits. Right, so we're going to be looking at a little bit at limits of composite functions, and actually I think this is actually a pretty good place to end this podcast. I'm going to end this podcast, and we're going to come back and look at properties of limits. All right, so bye for now.